Look around your room and convince yourself that the objects you see are unquestionably solid. The desk, the wall, and even your own hands appear to occupy real three-dimensional space. Yet some physicists suggest that depth may be nothing more than an exquisite illusion. According to the holographic hypothesis, everything inside the universe could be encoded on a distant surface. Think of reality as a brilliantly detailed movie projected from the cosmic edge inward. The idea sounds outrageous, but it springs from hard-won insights about black holes and information. In a hologram, every fragment of the film contains the whole image in lower resolution. Likewise, each tiny patch of the boundary might carry instructions for the entire cosmos. If that is true, existence is fundamentally about data rather than stuff. Space, time, energy, and even consciousness would emerge from patterns of bits on a gigantic screen. Tonight, we will journey through the science, the experiments, and the lingering mysteries of this theory. By the end, you may never look at the night sky or your own reflection the same way again. The first clue arrived when physicists asked how many ways a black hole could be arranged internally. Jacob Bekenstein realized that its entropy depends on the surface area of the event horizon, not the volume. Stephen Hawking's quantum calculations cemented the formula and linked entropy to horizon geometry. If information scales with surface area, perhaps the interior has no independent degrees of freedom. Gerard de Hooft and Leonard Susskind extended the logic to any region of space. They proposed the bold holographic principle. A three-dimensional world can be fully described by two-dimensional data. In other words, volume is an emergent mirage produced by a thin shell of numbers. This principle doesn't merely shrink reality, it reshapes the very meaning of locality. Events deep inside a region might secretly be controlled by pixels far away on the border. To visualize it, imagine living inside a snow globe, whose glass surface stores your entire life story. Open questions remained, but a revolutionary mathematical breakthrough would soon arrive. That breakthrough would convince thousands of researchers that holography isn't just philosophy. It is calculable physics. In 1997, Juan Maldacena discovered a precise duality between gravity in 5 dimensions and quantum mechanics in 4. The correspondence is known as anti-de Sitter, conformal field theory, or simply ADS-CFT. Calculations that were impossible on the gravity side became solvable on the boundary field theory. For the first time, theorists could compute black hole evaporation without a full theory of quantum gravity. The duality stunned the community because it showed that space-time may be a redundant viewpoint. Everything that happens in the bulk can be restated as a drama playing out on the edge. Researchers quickly applied the trick to quark-gluon plasmas, created at the Large Hadron Collider. They also modeled exotic superconductors, whose resistance vanishes through mysterious collective behavior. Perhaps most intriguingly, quantum information theorists noticed that ADS-CFT resembles an error-correcting code. In that picture, geometrical connectivity is nothing more than robust entanglement among logical qubits. If a region of space is lost, the code can rebuild it, just as a hologram reconstructs an image when cracked. Space-time, it seems, might be the ultimate form of data redundancy. Still, elegant equations demand experimental challenge, and laboratories have begun to answer the call. Ultra-cold atom setups can cool clouds of potassium or lithium to millionths of a degree above absolute zero. Lasers then trap the atoms in optical lattices, creating programmable quantum matter. Certain configurations emulate the Sachdev-Yekitaev model, thought to mimic black hole dynamics. In these tabletop universes, energy spreads at the fastest rate allowed by quantum mechanics. Researchers measure out-of-time order correlators to test predictions of holographic scrambling. If their data align with gravitational calculations, the laboratory and the cosmos will have shaken hands. Meanwhile, cavity QED experiments send photons bouncing between mirrors to observe synthetic horizons. The hope is to watch Hawking-like radiation emerge in a room-temperature apparatus. Even distant gravitational wave detectors contribute clues as they measure black hole mergers with incredible precision. Every new data point tightens or loosens the theoretical web that binds bulk and boundary. Progress is slow, but for a question this grand, patience is part of the exhilaration. One of holography's most beautiful lessons is that geometry may crystallize out of quantum entanglement. Slice a holographic universe into two parts and count the quantum links between them. The more entanglement you find, the larger the area of the minimal surface that separates the regions. This relation is captured by the Ryu-Takayanagi formula, a staple of modern quantum gravity research. Entanglement does not merely live in space, it creates space. Follow the thread far enough, and you discover that a wormhole is just a pair of systems maximally entangled. That insight spawned the slogan ER equals EPR, connecting Einstein-Rosen bridges to quantum correlations. It also hints that teleportation protocols may one day resemble opening tiny portals. Although such feats remain distant, quantum networks are already weaving small webs of entangled nodes. As these networks grow, they might teach us whether gravitational connections can be engineered in the lab. If so, the boundary between fundamental physics and quantum engineering will blur beyond recognition. In holography, science fiction keeps turning into future experimental design notes. So far, the mathematics works best in negatively curved anti-de Sitter space. Unlike our nearly flat universe, yet new formulations called DSDS and flat space holography aim to extend the principle to cosmology. Some researchers derive entropy bounds for cosmic horizons that mirror black hole area laws. Others search the cosmic microwave background for subtle fingerprints of boundary encoding. Gravitational wave astronomy might reveal whether space itself has a discrete pixel size. If area scaling rules survive outside a DS, the holographic principle could be truly universal. That would mean the night sky is not an infinite abyss, but the inner surface of a cosmic storage device. Every supernova, comet and cloud would then be a flicker on an unimaginably distant wall. Even time could be a bookkeeping protocol that orders when bits are accessed. The more we learn, the more reality begins to look like an enormous, self-organizing ledger. In such a universe, conservation laws are simply accounting statements about information flow. The laws are beautiful because the ledger never drops a single bit. Inevitably, the holographic idea nudges us towards the simulation hypothesis. If the cosmos is stored like software, could another layer of reality host the server? Maybe advanced intelligences can tweak the codebase and generate completely new physical rules. Our constants of nature might be default parameters chosen for computational efficiency. Consciousness, in this view, emerges when certain boundary patterns close a self-referential loop. Thoughts become vibrations in the datasheet, echoing inward as the sense of an inner world. Such speculation straddles physics and philosophy, but it remains logically possible. Meanwhile, neuroscientists study how information integration in the brain relates to subjective awareness. If this journey is sparking your curiosity, hit like, subscribe, and leave a mind-bending question in the comments below. Together we can map the boundary of knowledge, one pixel at a time. Remember, every question you pose may already be etched on the horizon, waiting to be read. So dare to wonder aloud. Returning to the lab, engineers are designing quantum error-correcting architectures inspired directly by holographic codes. These architectures aim to store information with gravitational robustness against noise. In parallel, mathematicians hunt for a unifying principle that will transcend ADS-CFT and subsume all dualities. The effort may rewrite string theory, loop gravity, and emergent spacetime programs into one grand synthesis. Funding agencies are quietly supporting detectors that can probe Planck-scale deviations in photon arrival times. If those anomalies appear, they could reveal the pixel lattice beneath smooth geometry. Even quantum computers might soon simulate miniature universes where bulk and boundary dynamics are visible in real time. High-energy colliders, gravitational antennas, and entangled sensor arrays will each contribute a piece of the puzzle. The scale of the project rivals that of mapping the human genome or deciphering the cosmic background. Yet the potential payoff is even larger, understanding why anything exists the way it does. Each step forward will test our humility as much as our cleverness. After all, decoding the universe is also decoding ourselves. Imagine standing on a beach at night while waves whisper against the shore. The stars overhead glimmer like pixels in a vast celestial monitor. Though you feel small, your capacity to reason connects you to the entire informational fabric. Every observation you make enriches the boundary's description of the bulk. In that sense, the universe needs observers to complete its own self-portrait. Whether we are characters or co-authors remains an open question. Future generations may wield technology powerful enough to edit local patches of the cosmic code. They might craft bespoke pocket universes with personalized physics inside quantum processors. If that future arrives, humanity will graduate from reading the hologram to writing it. Until then, we continue to peer at the shimmering edge, gathering clues and daring to dream. So the next time you gaze into the night, ask yourself, am I seeing depth, or am I decoding a perfect sheet of light? Either way, the mystery is worth every moment of wonder.